In this video, we're just going to walk through some of the important notes about right triangle trigonometry that we've covered in the last couple of lessons. A lot of this is review. In a right triangle like this, if I consider this angle right here to be theta, and these A, B, and C to be the side lengths, then we can compose these trigonometric ratios, the sine, cosine, and tangent. And these are the reciprocal trig ratios simply because the cosecant is just the reciprocal of the sine. Notice the sine of this angle is opposite over hypotenuse A over C, and the cosecant of this angle is just the reciprocal of that, hypotenuse over opposite, C over A. And same with the secant, that is the reciprocal of the cosine, and the cotangent, which is the reciprocal of the tangent. These should not be confused with the inverse sine, cosine, and tangent functions, which inverse functions are different than the reciprocals, and we'll get to that in a minute. But it's also interesting to notice that these trigonometric functions use function notation, which we've been studying. But when we take the sine of theta, we are taking this angle as an input to this function, and the ratio is what comes out. So sometimes when we have to solve for a side length of our triangle, we can use these trig functions pretty easily, and then we just solve for either the A or the C or the B. But sometimes we're asked in problems to solve for the angle, some angle like the theta. And in that case, we can still start with this relationship. Let's say, again, I'm just continuing with the sine. And then in order to undo the sine function, we use the inverse sine, which is this sine to the negative first power. And we're not actually raising anything to the negative first power here, but this is notation. This is how we write an inverse function. So the inverse sine, sometimes we call it the arc sine, but the inverse sine of the sine of theta is just theta, just as the square root of the square of x is just x, because the square root and the square functions, those are inverses of one another. In my equation, I've also taken the inverse sine of the right-hand side, and notice for the inverse sine function, it takes a ratio as an argument and returns or outputs the angle. So really what an inverse function does is it switches the outputs and the inputs of the function, and it'll map backwards from a particular output of the original function, this ratio. It will give us a particular value. There's other issues and important things we have to understand about inverse functions, but it's good as time as any to introduce that. I've got a couple of notes here. The inverse trig functions undo the trig functions, okay? And then also, we just want to get used to this notation. Here I've written f to the negative first power of x, which we really say the inverse of f of x is how we say that. And I've just described that here. The inverse, f negative 1 of x is really the inverse function of f of x. So this is the function that undoes whatever this function does. And we'll be studying a little bit more of that in this unit. Moving on here to a couple of special right triangles. Here, real quick, is the 45, 45, 90 triangle. And I've made a very specific 45, 45, 90 triangle with of course, those are the angle measures of this triangle. And because those two angles are equal, 45 and 45, this is an isosceles triangle, so the two legs of this triangle are also equal. And I just marked them as 1 unit. And using Pythagorean's theorem, we see that the hypotenuse is just the square root of 2. And we can, any 45, 45, 90 triangle is going to be proportional to this one. So what I've done over here is just imagine that I scale this triangle by a factor of a. Then these two side lengths, these two legs have length a, and then the hypotenuse is just a times the square root of 2. So this can be helpful in very quickly understanding what the side lengths of a 45, 45, 90 triangle are. If you know any one of these side lengths of this kind of triangle, then you can find the other ones pretty quickly. Here, for the 30, 60, 90 special right triangle, I begin by just drawing this equilateral triangle. And what makes it equilateral is that all three angles, and just ignore the line down the middle for just a minute, but each of the three angles in this big triangle are 60 degrees, and of course that makes it equilateral, and so the sides are all the same length. And I've given them this particular triangle a side length of 2 so that my numbers in this little exercise work out pretty nicely. What I do is I can divide this equilateral triangle into 2 congruent right triangles by drawing this elevation down the middle. And in doing so, I've made a 30, 60, 90 right triangle. And I kind of pull that apart right here. So this is a 30, 60, 90 triangle. And if we notice the dimensions of the equilateral triangle that I started with, this short leg has to have a length of 1 because it's half of 2. And then the hypotenuse is 2. And again, using Pythagorean's theorem, we can find that this remaining leg has a length of the square root of 3. And just like in the previous right triangle, special right triangle example, we can multiply all of the sides by a particular factor. And what we've done is we've just made a similar 30, 60, 90 triangle. In this case, it looks a little bit bigger. But again, if you know the length of any side of a 30, 60, 90 triangle, you can very quickly find the length of the other 2 sides. And that's also helpful because we can develop the trig ratios really quickly for the angles of 30 degrees, 60 degrees, and 45 degrees based on these 2 triangles. And so, and that's one of the useful things about the 30, 60, 90 and the 45, 45, 90 triangle is that we can really quickly understand or write the trig ratios without doing any kind of computation and without our calculators. So I've got a few special important notes over here. We've got special right triangles also are frequently used on standardized tests, so it's worth just memorizing really this information here and this information here and the relationship between the sides of these 2 triangles. They also offer a pretty diverse range of angle measurements for us to think about when we're trying to like maybe model something or map out a space. We've got 0, 30, 45, 60, and 90 degrees is really kind of the range of angles that we can, or I should say the set of angles that we can use just with these 2 basic triangles. And like I said earlier, calculations, particularly trigonometric ratios, are really easy with special right triangles. And we'll do one little example of that here before we finish this video. And what I'm going to do is just evaluate the sine of 45 degrees. And if you notice from our 45, 45, 90 triangles over here, the sine of 45 degrees is just the opposite, 1, divided by the hypotenuse square root of 2. And even if I use a different another 45, 45, 90 triangle, it just becomes a over a root 2, and the a's would cancel, and you either way you would reduce to this. So any triangle, regardless of any right triangle, regardless of its size, will ultimately, when we compute the ratios, we'll get the same thing. One of the things that we do with a number like this, when we have an irrational denominator, is we rationalize the denominator. And here I've done that. And the way I do it is I use the multiplicative identity. In other words, I just multiply this thing by 1. It's kind of like taking rewriting a fraction so you have a common denominator. So by multiplying the top and the bottom by the square root of 2, I get this, square root of 2 divided by 2. And now there's no irrational denominator in my fraction. And we do this for a couple of reasons. One, it's it's a lot easier to divide some estimate of the square root of 2, like 1.4. It's a lot easier to divide that by 2 than to divide 1 by some rational number, some estimate of some rational number. Also, it's easier to use this number in a calculation if we have to multiply this by something or add a couple of fractions together. It's easier if the denominator is rational. So that is the summary of the trigonometry of right triangles.